So, does anyone have any question or comment from the previous lectures? Does anyone have any comment on the quiz? It was okay for all? Okay, then let's get started. So, we've started now for the last few lectures. We have started looking at how we can analyze. In the first part of this segment, we looked at static systems. So let's say, for example, you have a container full of particles which are just stationary. Then how do you find out what is the stress distribution inside the particle, inside the container? And we saw that really, in addition to the stress equations, we need one more condition, and that is the condition of incipient failure, to be actually able to calculate what are the stresses in the system. Now we've gone ahead a little bit and we say, supposing things are really moving slowly such that friction forces dominate, then we'll call those as slow flows, and last time I had started talking about that. But before that, I gave a small derivation on how you can calculate stresses when you are dealing with particles. And if you remember, we had a simple derivation to just show that the stress is just given by the total of all the particles which cross this surface. And when we do the calculation, it just looks like this, which is Fij is the force between the particles, Xij is the distance between the centers of the particles, and V is the volume which you are considering. So we had done this small derivation last time. And earlier I had told you also about this LAMPS command, which you can use to get the stress per atom. This command actually gives you only this part on a per atom basis. Then you have to sum over all the particles and divide by the volume. Okay, so this was one thing. And then before the quiz started, I just very briefly gave you an overview of two approaches for slow flows. One is to simply use the same thing that we did for statics. That is, we assume that the density is constant and we assume that there is incipient failure at all points, and then we can calculate what is the stress distribution. The other approach is what we call critical state approach or the critical state theory. And I'll explain a little later why it's called critical state theory. But in this theory, there are three parts to the theory. One is there is a yield function which depends on the density and the principal stresses. Then there is a flow rule which relates the rate of deformation tensor and the stress tensor. These are the principal coordinates of the rate of deformation tensor D and the stress tensor sigma, and lambda is some constant to be determined. And then you have the coaxiality condition, which says that the principal axes of the stress and the rate of deformation tensor are collinear. So wherever your stress is maximum, that's where your deformation is also maximum. So these are the two approaches which we will look at. There may be others also, and but this gives at least some overview of how we can look at slow flows. Now let's look at, and the first approach, which is the more Coulomb approach, and see, how we can analyze that. So first we'll start off with the governing equations, and okay, so this is where we had stopped last time, and this is lecture number 18. And today is 6th of September 21. So the topic we are looking at is slow flow. And what we mean by slow flow is, this is essentially flow is dominated by friction. So that is the main force that we are worried about, the interparticle friction. And there is no other thing that we have to take into account. So in this type of case, what we have, what sort of governing equations can we use? So if we write down the governing equations, well, in general, we need the continuity equation or the mass balance equation, which is just, you remember this from your transport. So over here, rho b is the bulk density, that is the particle density times the solid volume fraction, and v is the velocity. So here is the first equation, and the second one is the momentum balance equation, written in terms of the stresses. And so this one will be just the same as what we write in fluid mechanics. These terms are the acceleration terms. And then you have the total stress. We are not separating into pressure and deviatoric stress. So this is the total stress plus rho b into g. Now these equations are exactly the same as what we used for static systems. If you have a static system, then of course the first term is just, both terms are zero because velocity is zero. And over here v is equal to 0, so you will just get the same equation that we used in the case of static systems. So these are the equations, and again, we have to sort of think of what are the unknowns over here. So the unknowns are essentially I just list them down, they are the density, the three components of the velocity, let's just write it as Vx, Vy, Vz, and then the six components of the stress, which are sigma xx, sigma yy, sigma zz, sigma xy, sigma xz, and sigma yz. So these are the unknowns, and if you count them, there's 1 and 3, 4 and 6, 10. So there are 10 unknowns. For a 3D system. And how many equations? If you see this, the continuity equation is just 1, and here there are 3, because it's a vector equation, so there are 3 components, so there are 4 equations. So you can clearly see we need several more equations if we want to solve this. Supposing we look at a 2D system. So this is the unknowns for a 3-dimensional system. What are the number of unknowns for a 2-dimensional system? We look at some examples of 2D systems. So here, if you see, there's rho v, vx, vy, and since it's 2-dimensional, so we'll just look at sigma xx and sigma yy, and then sigma xy. So all terms with z in them are 0. So you will essentially now, you see with this, you will have 1, 2, 3, 4, 5, 6 unknowns. And if you look at how many equations you have, is 1 is continuity, and 2, because it's a 2-dimensional system, so you have 2 components of the momentum balance equation. So 1 and 2, so you'll have 3 equations. Again, same thing, that you have a very large number of unknown quantities which you have to determine. So what does this mean, and what does this imply? What this implies is that you need what are known as constitutive equations. And these tell you what is the material behavior. For a Newtonian fluid, we know that simple equation of tau, or you can write the stress in terms of the rate of deformation tensor, and that gives us enough additional equations to solve the problem. For granular materials, we need a different set of constitutive equations, and one approach, if you see, and that's what I'm going to start with, is, let's say, if we look at the Mohr Coulomb approach, then you have rho b is constant, so that variable goes away, so you have one less unknown, and then you will have a yield function which will give you the additional equation that you require. So for example, for 2D, if once rho b is constant, then you simply have one less variable. So you'll have 3 equations, and then plus 1 for the yield function, that will be 4, and you will have something like 5 unknowns. Is that right? So we look precisely at how this works out and how we can essentially get all of the variables with just using these two things, that rho b is constant and using a proper yield function. And I'm going to do that using an example for which an analytical solution is available. And that example is slow flow in a wedge shaped hopper. And this is actually been solved by one of the very famous people in granular mechanics called Stuart Savage. He did this in 1965. And so what are the assumptions that he made? Okay, first of all, let me draw the system. So what do we mean by a wedge-shaped hopper? So you can imagine one plate like this and another plate like this. So these are two plates. And the granular material is between these plates. And if you, let's say, if you extend these plates, then they will meet at some point over here. And let's suppose this we take as to be the origin of our coordinate system. And we will essentially assume that the particles occupy this space where this radius is R1, and let's suppose this radius is R2. If we look at a plane that is going through the origin, this is the vertical line, then we can measure the angle from here and we call that angle as theta. And let's suppose the full angle over here is theta w. Okay. Now he made, just to simplify the problem, and so what is actually going to happen? The material, because it's in here, it's going to flow out and it will come out of the base. So because of gravity, the material will flow out. And now in practical systems, so actually we are looking at a two-dimensional plane of a three-dimensional system which has two plates like this. And this is a very common thing in industry. Many hoppers have this type of shape at the base, and then on top there may be larger container. But we are only interested in this part of it. And what he assumed is, first of all, constant density. Then he assumed that the incipient failure, just like what we did for the static system. So this is essentially applying the Moore Coulomb condition. But very interestingly, in addition to this, to simplify matters, he assumed that there is radial gravity. That means that the gravity is acting in the direction that I have shown with the arrows. It's not acting downward, but it's acting towards the origin of the coordinate system. This is just a mathematical simplification, because once you assume this, then instead of g cos theta, the gravity term just becomes g. So your theta gets eliminated. So this is a great simplification. And we also assume zero wall friction. So there is no shear stress acting on the side walls. Now, in this case, what you have is, because of this, what actually ends up happening is, because you have zero wall friction, you actually end up getting the shear stress, that is sigma r theta, to be equal to 0, and that actually means that sigma theta theta and sigma rr are principal stresses. So that is a great simplification. Okay. Why is sigma r theta 0? Because there is zero wall friction, so there is no shearing motion. This is very much like what we did for the Rankine problem, where there was no sigma xy, and so sigma xx and sigma yy were the principal coordinates, principal stresses. Okay, so because of all these assumptions, you get this simplification, and then since we have incipient failure, so from this zero wall friction, we get this, and then from incipient failure, what we get is that sigma theta theta divided by sigma rr is equal to k. So you can see that in some sense we have been able to eliminate some of our stress components. In fact, 2 out of 3 stress components have been eliminated. Now, in this thing, an additional assumption that you can make, because of radial gravity, what you'll have is that the velocity, which in general will have components in the r direction and in the theta direction, is just equal to Vr of r comma 0. That means that this is equal to 0. And this is a consequence of both radial gravity and zero wall friction. So you have a purely radial flow, and this depends, velocity depends only on the radius. So now our unknown quantities are just Vr and sigma rr, because once we know these two quantities, then we can easily get sigma theta theta, and we already know sigma r theta is equal to 0. So out of the 5 unknowns that we have here, so rho b is already known, it's a constant and given to us, so we have 5 unknowns over here. So one of the velocity components is 0, one of the stress components is 0, and through incipient failure we get one more stress component. So now we have 2 unknowns and we have 2 equations, and those equations are the continuity equation in, now we have to write this in cylindrical coordinates. Okay, so if we write down the full equation and then write down v theta and vz are 0, then the only term that remains is and that actually gives us that Vr is equal to A divided by R, and here A is a constant of integration which we have to find out. Okay. So this is the continuity equation, and of the momentum balance equation, there's only the R component which is, otherwise in the other component all the terms are 0. So what we get from the R component is that rho B VR dVR by dr, this is the left hand side of the equation, this is equal to divergence of the stress, that is d sigma RR by dr plus sigma RR minus sigma theta theta divided by R minus rho B into G. Now this is a consequence of using radial gravity, because now since we are looking at the R component, you see the gravity is in the radial direction, so you just get it as a constant. If gravity was acting in the Z, in the downward direction, then this would have become G cos theta, then all of our initial assumptions would fail. So this is our momentum balance equation. What is nice is we already know the velocity in terms of this constant A, and we also know sigma theta theta in terms of sigma RR through this constant K. So if we make those two substitutions, then you get minus rho B A squared divided by R cubed is equal to D sigma RR by dr plus 1 minus K So this minus sign comes in the gravity term because the gravity is acting in the direction that is opposite to the unit vector in the radial direction. So this distance over here is r, and so unit vector is er acting in that direction, and this is in the opposite direction. So you have a negative term. So now if you sort of simplify this out, you see that this is a very easy equation to solve. We've solved this already, or a very similar thing, using when we did the stress distribution in a rectangular bin. We also we had a very similar problem, which was an inhomogeneous first order ODE. So we have to solve for this equation. This is a simple equation to solve, and again you can just do it using this integrating factor method. So you want to basically combine these two terms. So if I do this again, you see it's 1 by f d by dr of f times sigma rr. This should be equal to the right hand side. If I open this out, this will give us d sigma rr by dr plus sigma rr divided by f into df by dr. Okay. So these two terms should be equal to this. So you can see clearly that this is the same as this. So your f should essentially be 1 minus. So this essentially gives us, this implies that the integrating, to get the integrating factor, you must have 1 by f pf by dr is just equal to 1 minus k divided by r. which is something that can be easily integrated. So this gives you ln f is just equal to 1 minus k into ln of r plus some constant of integration, which is not important. And so now if we take the exponential on both sides, then you can just see straight off that f is just equal to r raised to the power of 1 minus k. So this is our integrating factor. So now if we substitute for that, then these two terms can easily be combined. And what you will get is 1 upon r raised to the power of 1 minus k d by dr of, so this is f times that, so it's r into 1 minus k times sigma rr is equal to rho b g minus rho b into a squared divided by r cubed. So now this is very straightforward. You just multiply throughout by r raised to the power of 1 minus k, and then you can try and integrate it. So you will get r raised to the power of 1 minus k sigma rr is equal to rho bg into r raised to the power of 1 minus k plus 1. So that becomes r raised to the power of 2 minus k divided by 2 minus k minus rho b into a squared raised to the power of r raised to the power of minus 2 minus k, and then you have to add 1 to that. So this becomes minus 1 minus k divided by minus of k plus 1. So this minus minus will cancel out, so it becomes plus here. And then you'll have one more constant of integration, which will be plus b. So you have two constants of integration, a and b. And then now I can divide throughout by r raised to the power of 1 minus k. So, you get a simple relationship here that sigma rr is equal to rho b g into r divided by 2 minus k plus rho b a squared. Now here you can see this is just going to be r raised to the power of minus 2 when you take this on the other side, divided by k plus 1, and then finally you get b divided by r raised to the power of okay. So this is the solution. You have two unknown constants over there, and so we can apply boundary conditions. And the boundary conditions are that sigma rr is equal to 0 at r equal to r1 and r equal to r2. So this is the simple boundary condition that we apply, that both at the exit and at the top surface the normal stress is 0. So through these two boundary conditions we can get the two constants a and b. And so we can try and do this where we have 0 is equal to rho b g r1 divided by 2 minus k plus rho b a squared divided by k plus 1 r1 squared plus b divided by r1 raised to the power of 1 minus k. And we also have the same equation but with r2.
I didn't catch that. Could you try again?
So it's exactly the same equation because all we are doing, because it's the same. The stress is 0 at both R1 and R2. So obviously you will have exactly the same equation for both. And now we can, what I'm really interested in is getting what will be the velocity. And if I want to know the velocity, I must know what is A. So supposing as a first step, I eliminate B from here. So I can subtract out this from this. So then what I will get is 0 is equal to rho b g divided by 2 minus k into r1 minus r2. Now r1 is smaller than r2, so this will be a negative number, plus rho b a squared divided by k plus 1 into 1 by r1 squared minus 1 by r2 squared. Now r1 is smaller than r2, so this is going to be a positive number. So, if we do a little bit of rearrangement, you can see first of all that rho b cancels out, and you will get a squared divided by k plus 1 into, now if I take the common denominator as r1 squared r2
Sir?
squared. Yeah.
We have to multiply equation 1 by r1 to the power 1 minus k and equation 2 by r to the power 1 minus k, and then it will be 0, right? The subtraction.
Right. I made a mistake in that. Okay. Thank you. I was going totally wrong. Okay, let me go back. Thank you very much. Yeah, if I want to eliminate that term, absolutely right. If this term has to be I should first multiply throughout by. Oh, I shouldn't have I shouldn't have rubbed out everything. Okay, these two equations are correct, right? These two equations are correct, but this is not. So I'll delete this. These two equations are correct. Now I should multiply throughout by r1 raised to the power of 1 minus k, and here I should multiply r2 raised to the power of 1 minus k and then subtract. So if I do that, so then let me write those equations again because I'm sure to make no mistakes. Rho bg r1 raised to the power of 2 minus k divided by 2 minus k plus rho b a squared divided by k plus 1 into r raised to the power of r1 raised to the power of, here I should, or maybe I just put it as 1 by r1 raised to the power of k plus 1 plus b, and this one will be the same equation but with r2. Okay, is this correct? Now I'll do the subtraction. And so what I'll get is 0 is equal to rho b g divided by 2 minus k into r1 raised to the power of 2 minus k minus r2 raised to the power of 2 minus k plus rho b into a squared divided by k plus 1 into 1 by r1 raised to the power of k plus 1 minus 1 by r2 raised to the power of k plus 1. So like this, we can see that rho b now will cancel out. And you'll get something that is quite complicated. So what do you get? So now if I simplify things out a bit, I'll get a squared. So, you know, I'm going to define, let's call this ratio, I'll call a ratio, just some number, alpha is equal to R1 by R2. Okay. So, and what I'll do is I'll try and eliminate R2 everywhere as just R1 by alpha. So I'll work only in terms of R1. And so this will give me 0 is equal to G divided by 2 minus K into R1 raised to the power of 2 minus K minus R1 raised to the power of 2 minus K divided by alpha raised to the power of 2 minus K plus A squared divided by K plus 1 into 1 by R1 raised to the power of K plus 1 minus alpha raised to the power of K plus 1 divided by R1 raised to the power of K plus 1. Okay, so little bit more algebra and we'll be done. So then now we can take a squared on this side, and this is a squared into, I'll take out r raised to the power r1 raised to the power of k plus 1 as common, and so I will get then 1 minus alpha raised to the power of k plus 1 over here, and this side is equal to, I'm taking k plus 1 on the other side, into g, and this I'm going to put it as k minus 2, so I'll take the minus sign inside, and I'll take out r raised to the power of 2 minus k, and then what I'm left with is 1 upon alpha raised to the power of 2 minus k minus 1. And so finally, if I take r raised to the power of k plus 1 on the other side, then I'll get some simplification. So I'll get a squared is then equal to k plus 1 divided by k minus 2 into g r1 cubed. And then this one I can write it as alpha raised to the power of k minus 2 minus 1 divided by 1 minus alpha raised to the power of k plus 1. So this is what you have. Now alpha is always going to be, somehow I've made some mistake somewhere, and I don't know, there's a minus sign that is somehow missing. So according to my notes, I've only written down the final expression that this should actually be 1 minus
Sir,
alpha.
after defining alpha, the next step r1 raised to 2 minus k minus r1 raised to 2 minus k by alpha raised to 2 minus k. So when we take r1 raised to 2 minus k outside, 1 minus alpha raised to k minus 2.
I think good that you caught the mistake, but this is the final result that I get, because finally we know alpha is always going to be less than 1 because r1 is much less than r2. So alpha is always going to be less than 1. That's why, both of these, this term in the
second last step in the right hand side, it should be 1 minus 1 by alpha to the power 2k.
Okay. You're right. I wrote it the other way around. Okay. Okay, so that's why, that's the big mistake. That is just, silly mistake. I don't know why I put it the other way around. 1 minus
1 minus 1 by alpha to the power 2 minus k.
No, but then I take it. Okay. Right. That is correct. I did the minus sign twice. I put 2 minus k, I made it k minus 2, and then I again did that. So that's right. So it should actually be 1 minus alpha raised to the power of 2 minus k. And then it's okay, right?
Yes, sir.
And so then I have to take out alpha raised to the power of 2 minus k also, no? Somewhere?
No, it will be 1 minus alpha to the power k minus 2.
Perfect. This is correct. So now this derivation, what I have done after many mistakes, is correct. But now through all this, we can get what is a, which is all this raised to the power of half. this raised to the power of half. And really the key result then you get is that the velocity, radial velocity coming out, and actually A should be negative. Why is A negative? Because if you see this, the velocity is in the negative direction. So VR is in the negative direction, so A is negative. So you get VR to be just equal to, and here what we say is, supposing alpha is much greater than 1, and of course k is greater than 2. In that case, both these terms containing alpha will disappear, and so then what you will be left with is just VR is just equal to A by R, and if we substitute for A over here, this is minus of k plus 1 divided by k minus 2 into G R1 cubed raised to the power of half into 1 by R. So if you want to find out the velocity at the exit, then what we get is that VR1, which is velocity at R1, is just equal to minus k plus 1 divided by k minus 2 into G R1 raised to the power of half. So this is really a very nice result, because it says actually two things which is observed for these kinds of systems. The first result, of course, is that the flow in the system is independent of the height. So you can see that R2 is the height of material inside the hopper. And so if your height, if R1 is much smaller than R2, then really the flow rate, because the radial velocity will determine the flow rate. The flow rate is independent of how much material you have in the hopper, and this is very much like the problem we solved for the stress distribution in the bin with sidewall friction, where once you go beyond a certain height, then the height doesn't matter. And this is what we see here for the flow rate also. And what is also very interesting is that the flow rate simply depends on gravity into the size of the orifice raised to the power of half. So you don't care about any of the other things in the system. It doesn't depend on the angle, it doesn't depend on anything, it only depends on this and the angle of internal friction, K, which determines K, because we know K is 1 plus sine beta divided by 1 minus sine beta. So this is the very nice result that is obtained, and he Savage compared it to some of the experimental systems, and he found that there's some reasonable agreement. And I'll try and show you. We have also been doing now. We have power of DEM, so we can easily compare. And many of these assumptions actually are correct. And the flow does turn out to be like this, even if you do DEM simulation in this system. So there's a PhD student who is working in our lab, and she's Afroz. She's doing simulations of this, and she's done detailed simulations for many different parameters. And I will show you some results next time of this. Okay, so see, in the next, on Thursday, I'm going to have one more quiz, which will be almost on the same pattern as the first one. And I think that will be a nice way for you to revise the second half of what I've taught from 7 to 13 lectures before the mid-sem. Because we are in slot 1, uh, this mid-sem is the first mid-sem, and it will be on the 11th. And the material covered in the mid-sem will be whatever is done in quiz 1 and quiz 2, that is from 1 to 13, that is up to statics. I think that's up to statics. Maybe one or two lectures more. I'll give you precisely up to which lecture. So up to lecture 16. That's where the mid-sem will be up to. So we had in the quizzes up to lecture 13, which is up to the Morse circle. But then for the mid-sem, I'm going to include this part as well. And so we'll not consider the slow flow part, but everything up to lecture 17 will be in the mid-sem. Okay. As the pattern for the mid-sem will be that there will be problems that you will have to solve. There will be some questions that you will have to answer, short answers, and you have to do it on pen and paper, scan and then upload onto Moodle. The mid-sem will also be open book, open notes, whatever, and there will be proctoring, the same as what we did for the quiz. Okay. Okay, so if there are no questions or doubts, then let us end. So thank you and see you.